Hello, welcome. Thanks for this opportunity to speak here. Unlike other presentations, this is not so much of a research work, it's more of an engineering work. So thanks to the reviewers, for giving us this opportunity to talk about it. And we hope with my colleague Tomek to bring up something in terms of the discussion about having a more system-level approach to designing tinyML and all IoT solutions. So this is a typical thing for how an IoT solution is being created. We are working closely with IoT developers, and what we see is that a lot of these solutions are failing in the POC phase. And in fact, here we are citing this Beecham research from the last year that talked that about 3 out of 4 IoT projects are considered to be a failure by IoT solution providers. So in a typical scenario, there is a MCU, and to MCU is added a modem. There are sensors that needs to be integrated. If there is a cellular device, there is also a SIM card, which is another layer of complexity. There are antenna providers. And then there is a network, there is the whole, cloud part with data platforms. All of these solution providers in the first place think only about gathering as much data as they can. If they are smart enough, they are also thinking about OTAs, over-the-air updates of the firmware in order to fix the bugs. And there are like tinyML platforms for tinyML solution or any other platforms. But what we see is that there is a multitude of component vendors, and these components need to be integrated together, and multitude of cloud connections. And for these really constrained devices, the number of concurrent connections that can be opened is also restricted. So this is all very challenging if you think about this kind of sustainable, robust solutions. So we have been thinking about what kind of requirements robust solutions should have it, and these are the 4 ones that we have agreed on. One is about the usability. So this means that the deployed system especially needs to be easily to operate, and the response to be thinking about ops tools during already the design phase of the IoT solution. Interoperability, and this is something that is very often ignored. And interoperability, because IoT solutions are usually coming, are working on the intersection of electrical engineering, mechanical engineering, all these things. And these different industries from software engineering, for those guys, interoperability, open standards are important. So we try to bring attention to the necessity for having some standardized based approaches. And especially, on this, emerging markets where lots of companies are up and down, changing acquisitions, lots of the things, we see that some of these vendors are getting, into trouble because the solution they have been built on cannot be maintained in the long term. Sustainability, as this was already mentioned in the keynote speech, and security as well, as lots of these guys don't think about security at all in the very first place, and once something goes wrong, then they are panicking. So, what are we proposing? The right part is this, MLOps, the famous illustration, the famous figure from this paper by Harvard and Google about, making tinyML widely accessible. And we have added this left part about, lightweight machine-to-machine protocol, which is the communication protocol for managing lifecycle management of IoT devices. And the right part is about collecting data, training, doing AutoML, testing, and deploying, but more in this kind of controlled environment. And what we are advocating is going into these deployed devices. So to do the deployment, you need to have this over-the-air, firmware over-the-air, doing in a secure way, to bootstrap a device, and then from the IoT device you get this bootstrap device phase. And then once the device in this operational state, it keeps gathering data, you are getting this kind of information, how well is your tinyML model, how well is your solution doing. So you get the scores, this gives you the insights based on the tools that we have created, and then these insights can be pushed to the cloud for further enrichment of the data sets, retraining improvements. There can be very interesting things because we see that environments or the assumptions behind the delivery of the model has been changed between the laboratory training situations and the actual in-the-field deployment. And then the other aspect is this manage part, where based on the insights, lightweight machine-to-machine allows you to tweak some parameters, some configurations in a lightweight, instead of doing the full over-the-air or full flash device reprogramming. Based on this, you could enrich your solution. So our proposal is the combination of two things. One is the FogML, which is the framework that my colleague has written, and this is just an open source framework for generating tinyML code, so sort of like AutoML. It's not based on the deep learning, so it's just based on the classical algorithms. And the second one is joining this with lightweight machine-to-machine client and the lightweight machine-to-machine platform. Based on this, you have just one connection, so you don't suffer from the multitude connection between the device and the server and the cloud part. And then behind the lightweight machine-to-machine platform, you could be putting all of these interesting platforms in the cloud for data, for tinyML, and all of these things by integrating this into one communication framework. And then lightweight machine-to-machine client on the device can be acting as the dispatcher for different apps like FogML or any other apps as the developers are building. So, and finally, based on these communication semantics that we have created, for this tinyML operational insights, we have created mechanisms for reporting aggregated classification results, detecting anomalies, measuring magnitude of these anomalies, and also for efficient machine learning model updates, not just over-the-air full device reprogramming, but like parameter tweaking or partial reprogramming when, for example, just the number of hidden layers in the neural network is changing, but the actual input and output remain the same. All of this requirements of the usability, these are just the tools, this communication semantics that we have developed on top of lightweight machine-to-machine, together with the integration with the hardware and with the tinyML platforms. Interoperability, everything is open source based. Sustainability, lightweight machine-to-machine brings this energy efficiency, and also flash size reduction, since you are just introducing one network stack in a device instead of multiple, so you are reducing the amount of the flash consumption. And finally, the security by doing our deep integrations with the trust zone and hardware security models. I'm sorry, I think I went over time, but it's really, really tough, to squeeze this in. Oh, sorry, I'm very happy, for this presentation. I'm happy also to answer all the questions, and thank you for this opportunity.